Okay. So today we are going to discuss about crystal field theory in coordination compounds. We all know that coordination compounds have various characteristics and so far in the theories that we have discussed across this lecture, we have seen some limitations to each and every theory. So there is crystal field theory which addresses to most of the limitations that other theories have to say about coordination compounds. And crystal field theory is explained differently for the tetrahedral and the octahedral complexes. So firstly, we are going to discuss about the CFT in octahedral complexes. From the name itself, it is very obvious that the octahedral complexes have 6 ligands surrounding the central metal atom. Now, let us consider that this is our central metal atom. Now, it will have 6 ligands that would be willing to donate their lone pair of electrons to this metal atom. So, let us say these are those ligands: L1, L2, L3, L4, L5, and L6. Now, one very important consideration that the crystal field theory uh, takes is that it treats everything as point charges. So, typically, we are dealing in terms of electrostatics. So, the metal atom is considered as a point charge, and the ligands, all the ligands are also considered as point charges according to crystal field theory. Now, since there are 6 ligands surrounding the metal atom, crystal field theory says that in an octahedral complex, all the ligands approach the metal atom via the axis. That means these are the axes that we have. We have the x-axis, y-axis, and z-axis. I'm representing z in this manner. So now, in an octahedral complex, all the ligands approach the metal atom via these axes. Now, let us just have, since we are talking about coordination compounds and hence the metals or the elements that are involved over here are the D block elements. So obviously we are more concerned, or we are going to learn more about the D subshell here. Now, if we have a look at the D subshell, that is D, the degenerate orbitals of D are dxy, dyz, dzx, dx square to y square, and dz square. And since it is said that the ligands in an octahedral complex approach the metal atom via the axis, now the two orbitals that are present along the axis are dx square to y square and dz square. Now let us have a look at how these orbitals look like. Dx square to y square looks something like this. This is how dx square to y square looks like. Now dz square looks like this. So basically here this is the x-axis and this is the y-axis, and here this is the z-axis. So since these two orbitals are inclined along the x, y and z axis, these are the axes which are going to be, in fact, sorry, these are the orbitals which are going to be the most affected in this process of ligands approaching the metal atom according to the crystal field theory, because here we are treating everything as point charges. Now, in now let us consider the ligands are approaching the metal atom via the axis. All the 6 ligands would be approaching along the positive x, positive y, uh, positive x, positive y, positive z, negative x, negative y, and negative z. Now, since the ligands that are approaching the metal atom have electrons in them, and the metal that is having these orbitals also has got electrons in its shells, there is some sort of interaction, I must say there is a kind of repulsive force acting between the electrons of the metal and the electrons of the ligand. So when the ligands are approaching the metal along the axis, because of this repulsion force, the what happens is, see, this is the regular d orbital or the d subshell that we have. It has got its 5 degenerate orbitals. The meaning of degenerate is that all the orbitals in the d subshell have the same amount of energy. Now, in the process where the ligands are approaching along the axis, because of the repulsive force that is acting between the ligands and the metal atom, the degeneracy of the d orbital will be lifted. That means the d orbital will no longer be a degenerate one, it will become non-degenerate, in the sense that, since I already told you that the ligands are approaching along the axis and the orbitals that are present along the axis are bound to face the maximum amount of effect. Because of this, because of the repulsive force, the energy of the dx square to y square and dz square is lifted, and thereby the energy of the xy, yz and zx which are present between the axis is lowered down in order to conserve the energy. Since energy is neither created nor destroyed, it's just conserved in the process. In order to conserve the energy in the process, the dx square to y square energy, let us say this is the energy x at which the degenerate d subshell is present. After the interaction between the ligands and the metal atom, the dx square to y square energy will be lifted to this extent, and the dxy, dyz and dzx energy will be lowered down, whereas this is the midline. It is not how much ever extent has been increased, that much extent will be decreased in the process in order to conserve the energy. Now, this is how it goes for an octahedral complex, and using this concept of crystal field theory, we can also explain the coloration in the coordination compounds. Now see, here the distance that between the non-degenerate d subshells is lesser. There is a higher chance of the electrons involving themselves in an electronic transition. So during this process of electrons jumping from the lower energy d subshells to the higher energy d subshells, and then again coming back to their original subshells, there is an amount of energy that is absorbed and released, and it is in this process that uh, it is this process that explains the coloration of the coordination compounds, which the valence bond theory could not explain. And one more thing is that these three orbitals are together called the T2G orbitals, and these two orbitals are called the EG orbitals. T2G stands for triple degenerate orbitals and EG stands for evenly degenerate orbitals. And this distance that is present between these two non-degenerate orbitals of the d subshell is denoted by delta O. Delta O. This delta is known as crystal field stabilization energy, CFSE, and there is a O in the subscript which indicates that this energy is the one that represents the octahedral complex CFSE. Similarly, similarly, the theory is also explained with respect to the tetrahedral complexes, which we will discuss later.